Every library in the world contains books the librarian has never read. Ask the librarian where to find information about a specific topic, and they do not need to have read the book to provide the trusted answer. They need to know how the library is organized. A language model without RAG is a librarian who has read everything in the building up until the day training ended. Consider that new content is being delivered continuously. Every new document, article, image, and volume that arrives after the last training date sits in a receiving dock, unread, inaccessible, as if it does not exist. RAG is the receiving dock with a retrieval system attached. New content arrives, gets indexed, becomes immediately available for the next query. The librarian does not need to reread the entire library to know what came in this week. The retrieval system handles that. The model's weights do not change. What the model can reach does. The documents in the receiving dock stay there, available at retrieval time, until the next training run when they move from the dock into the librarian's permanent memory. RAG keeps the knowledge living, training makes it resident. This is what RAG is and why it comes first. Models, Part 13. The model knows what it was trained on. RAG is how it knows what you need it to know. Section 1. The problem RAG solves. A language model's weights encode what it learned during training. That training had a cutoff date. Everything that happened after that date is invisible to the model unless it is provided at inference time. For a pipeline built on a dataset like NOAA storm events, which is updated continuously and covers specialized operational records the model was never trained on, the training cutoff is not a minor limitation. It is a fundamental architectural gap. The gap has a second dimension beyond recency. Even for events that occurred before the training cutoff, a model trained on general internet text has shallow coverage of specific operational datasets. The NOAA Storm Events database contains granular county-level records, specific damage assessments, and forecaster narratives that did not appear in the model's training corpus in any meaningful volume. The model knows what a tornado is. It does not know what happened in Jefferson County, Alabama, on April 27, 2021, unless that specific event was in the training data, which it most certainly was not at the level of detail your pipeline requires. RAG closes both gaps simultaneously. It makes post-training information available by retrieving it at inference time. It makes specialized operational data available by building a retrieval index over your specific corpus. Neither capability requires touching the model's weights. Section 2. How RAG works. RAG connects three components that earlier articles in this arc built independently: the embedding model from the stack article, the vector store from the data pipeline, and the language model from the serving layer combined into a single inference flow that runs on every query. When a query arrives, the first step is query embedding. The same embedding model that processed the NOAA documents during ingestion processes the user query and produces a vector representation of the query's meaning. This is the bridge between natural language and the vector space where retrieval happens. The second step is retrieval. The query vector goes to the vector store, which finds the stored document chunk vectors most similar to it. Similarity in vector space means similarity in meaning. A query about hail damage in the Texas Panhandle produces a query vector that sits close in the vector space to chunk vectors from NOAA records describing hail events in that region. The vector store returns the nearest neighbors, the chunk whose meaning is most similar to the query, ranked by similarity score. The third step is context assembly. The retrieved chunks are placed in the context window after the system prompt and before the user query. The model now has access to specific storm event records most relevant to the question being asked. The token budget management from Part 12 governs how many chunks fit and in what order they are placed. The fourth step is generation. The model reads the system prompt, the retrieved context, and the user query, and generates a response grounded in what the retrieved documents contain. The weights determine how the model reasons over the context. The context determines what the model has to reason over. This four-step flow, embed the query, retrieve relevant chunks, assemble context, generate response, is what RAG means in practice. The concept is straightforward. The implementation decisions within each step are where the complexity lives. Section 3. Why RAG before fine-tuning? Part 7 established the conceptual distinction between RAG and fine-tuning. RAG gives the model access to information it was not trained on. Fine-tuning makes the model better at reasoning over a specific domain. The distinction matters for sequencing. RAG is faster to implement. The data pipeline built in Part 6 and 7 is the foundation. Adding an embedding model and a vector store to the serving infrastructure is a day of work, not a month. Fine-tuning requires preparing a training dataset, running a training process that takes hours on consumer hardware, evaluating the fine-tuned model against the base model, managing the resulting weights as a new model version. The time investment ratio between RAG and fine-tuning for a first deployment is roughly 1 to 10. RAG is easier to update. When new NOAA data becomes available, updating the RAG pipeline means adjusting the new records into the vector store. The model weights do not change. The update is additive and reversible. Updating a fine-tuned model with new domain data requires retraining, which risks degrading the adjustments the previous fine-tuning produced if the new training data is not carefully balanced against the original. RAG is more transparent. A RAG response cites the specific documents that formed it. The source event records that contributed to a response are identifiable and verifiable. A fine-tuned model's domain knowledge is encoded in weight adjustments that cannot be traced back to specific training examples at inference time. For a use case where response provenance matters, RAG provides it by design. Fine-tuning does not. RAG has a ceiling. It can only reason over what it retrieves. If the relevant information is not in the vector store, or if the retrieval step fails to surface it, the model answers from its training weights or acknowledges the gap. Fine-tuning raises the floor by improving the model's baseline capability in the domain regardless of what retrieval surfaces. The right production systems use both. RAG first because it delivers most of the value fastest. Fine-tuning later when RAG alone is not enough. Section 4, where RAG fails. RAG is not a complete solution, and understanding its failure modes before building it is what separates pipeline that works in a demo and one that works in production. Retrieval quality ceiling is the primary failure mode. The RAG pipeline is only as good as what it retrieves. If the embedding model produces poor vector representation of domain-specific content, or if the chunking strategy fragments documents in a way that loses context, the retrieval step surfaces the wrong chunks. The model then generates a response grounded in irrelevant or incomplete context. The response will be coherent, it will not be correct. The failure mode is invisible without evaluating. This failure mode is invisible without evaluation against known correct answers. Chunk boundary problems occur when the relevant information spans a chunk boundary. A NOAA storm event narrative that describes a tornado's path across 3 counties may be split across 2 chunks by the chunking strategy from Part 6. A query about the full map retrieves one chunk and misses the other. The 50 token overlap specified in Part 6 mitigates this but does not eliminate it. Events with usually long narratives or complex multi-county paths are candidates for this failure. Context window competition occurs when multiple retrieve chunks contain partially relevant information and the most relevant context ends up in the middle of the context window where model attention is weakest. The loss in the middle problem from Part 12 is a RAG failure mode as well as a budget management problem. Retrieval ranking by similarity score does not guarantee that the highest ranked chunk is the most useful one in the specific query. Re-ranking strategies that apply a second relevance filter after initial retrieval mitigates this at the cost of additional inference latency. Contradictory context occurs when the retrieved chunks contain conflicting information. The NOAA records for the same event updated across multiple annual files may contain revised damage assessments that contradict earlier figures. The model receives both versions in the context window and must either reconcile them, which it may do incorrectly, or surface the contradiction explicitly, which requires the system prompt to instruct it to do so. The data pipeline's deduplication step from Part 6 reduces but does not eliminate this failure mode. Section 5, the embedding model decision. RAG requires the embedding model to convert text into vectors. The embedding model is a separate component from the language model and deserves explicit selection rather than default exception of whatever the framework suggests. 2 properties matter most for embedding model selection in the NOAA pipeline. First, the embedding model should be trained on text that resembles the domain. General purpose embedding models trained on web text produce reasonable vectors for most content. Embedding models trained or fine-tuned on scientific and technical text produce better vectors for domain-specific terminology. Second, the embedding model's vector dimensionally and the vector store's index configure must match. An embedding model that produces 1,536 dimensional vectors requires a vector store index configured for 1,536 dimensions. For the NOAA pipeline, a general purpose embedding model is the right starting point. The domain-specific terminology in Noah narratives specialize but not so far from general English that a general-purpose embedding model produces meaningfully degraded vectors. The assembly article in part 16 makes the specific selection with full reasoning. Next, the RAG pipeline against the Noah corpus with Claude code prompts at each step. The embedding model gets selected and configured. The vector store gets populated from chunks from part 6. The retrieval layer gets wired to the serving information from port 16. The first end-to-end query runs against real Noah data. The concept is clear. The next article makes it executable.